All right, nobody else is coming, then we have to start. So welcome to the algorithms. What shall we do and how we shall do it? First of all, I have to show you the web page, which will be the basis of our, let's say, every day or every week activities. So the web page is located at standard courseware pages of our faculty. The address is up there. And what's there? First of all, there are some course goals. Well, what are the goals? Do something about algorithms, do a bit programming, and that's it. We need some prerequisites, so everybody is expected to be able to do a little bit programming. You don't have to be extremely skilled. On the other hand, what do they say? Well, capable of programming at least in one of languages: C, C++, Java, Python. Mostly, as I understand it, nowadays people are shifting towards Python. So we'll have the seminar, so we'll talk about the details there. I'm just curious now, who is willing to do programming in Python? Please raise your hand. 1, 2, 3, 4. The rest of you are into C or Java. Who is into Java? 1, 2, 3, 4. Who is into C or C++? C++. All right, fine. So we have rather mixed audiences, which is probably better than anything else. All right. So what will be that? I have no idea, in fact, what we have to do. There will be some lectures, there will be some seminars, and there will be an exam at the end. So, step by step. Lectures, what are we going to talk about in the lectures? The lectures are listed here, and there are topics we will talk about during the semester, and we will come to them as time goes. So at the moment, just to let you know that it is there. The slides are there. There are some code examples for particular lectures down below. I am relatively afraid that they are in Python mostly. Yeah, open with, and they are mostly in Python. We don't have them in C or anything else, because last year this course was aimed mostly at people who are just Pythonists, so there it is in Python. On the other hand, for those who are not into Python, the Python in our lectures is relatively simple, so it is easy to understand. There is nothing extra Pythonic complicated. So I hope it will be clearly, easily readable for anybody coming from a different language. So as you might see, what's going on there? They define some function with some parameters. Parameters are not typed in Python, so you don't know what type of that parameter is. The type Python figures it out for you. And then there are for loops, return statement, assignments, function calls. The line starting with the hash sign is a command, and that's also rather simple to understand. So I hope this will not be a problem. So let's close this and just jump back to the course. So there will be lectures on various topics. Next, there are the seminars. That means the practices. Let's say, and what we will do there. First of all, and probably a very important part of the whole course are the homeworks. The homeworks are programming homeworks. you will be given some kind of assignment, some specification of the problem, and example data, and then you will have to produce a code which does solve the problem and submit that code into our upload system, which is referred to here. There is a link, and the upload system takes your code, runs it on some data which you even do not know. You will never know what kind of data are there in the system, and tells you how successful your code was. That is, whether it produced a correct result. That's first part. And the second part is that it has to do it also quickly. So your code has to be fast. We will see today an example of a fast code and a slow code, so you will get an idea what does that mean. So those homeworks will be graded. There will be 6 of them, and the grading scheme is down below here. Each homework, when you submit it, the system checks it and runs your solution on 10 test cases unknown to you. And if your code works correctly on all 10 test data sets, then you get 2 points. And if you fail on one of those 10 test cases, then you get only 1 point. And if it is less successful, then you are not successful. In such case, you say, that's bad. You look into the system, say, it's not working. So then you again have to check your code, try to improve it, and submit it again. So you can, of course, resubmit as many times as you want. What is important also are the deadlines. There are the deadlines, and they are meant to be deadlines. So please be careful and stick to those deadlines. If you submit anything after the deadline, sometimes it is even impossible to submit after the deadline, then you automatically have no gain from that homework, no points, and that's not a good idea. So if you have any kind of troubles, if you know that you are leaving for another country, or going home for some time, or maybe you fall ill, or anything like that, please negotiate it in advance with me. Anything can be agreed upon if it is in advance. If you come late, sometimes it happens that somebody comes at the end of semester and says, I could not be here, I had to go to Mars and then to Antarctica, and then we say, okay, it's too late. It cannot be helped whatsoever. So there are the deadlines. So we will start next week with those, as they say here, next week with those homeworks. Part of homeworks is the problem, no, it's not a problem, it's the issue of cheating. So if you choose to cheat, if you choose to copy your solution from somebody else, then, well, it's up to you if you choose to do so, but the upload system checks it, and I do check it as well. So we have the rules of so-called plagiarism, or in other words, of cheating. And please read them after sometimes during the semester, because they are rather important. What do they say here? What is most important, that when you write your homework, you are expected to write your own code. So the code you submit into the system has to be typed in by you and to be developed by you, the code itself. On the other hand, the idea of the solution, the general algorithm, how to do this part, how to do that part, That is, on the other hand, desirable that you discuss it with other people as well. You do some research on web or anything like that. You might even ask me if you are brave enough. So that's that part, the theoretical and analysis of the problem, is important, and you have to, and it is good if you do it with other people. When you get the understanding of the problem, you say, aha, this is done this way, and this that way. Then you have to code it yourself. Do not share the code with other people. So that's the basic rule how to work on the homework. So in case something goes wrong in this respect, we say that we do not guarantee that we are able to differentiate between the original work and plagiarism. So if you, in goodwill, give your solution to somebody else, so you say them out. Here it is. You will now also have a nice solution, so it does not work this way. So that's more or less about cheating. And probably that's nearly everything. Aha, how many homeworks do you have to solve? It has to be stated somewhere here. You have to obtain at least 8 points, and there are 6 of homeworks. Each maximum is 2, it has 12. So you can get at maximum 12 points, and you need at least 8 points. With, of course, be careful with the deadlines. So those are seminars, and those are a homework part of the seminars. Otherwise, the seminars, we will have one after this lecture immediately. What we will do there, we will mostly talk about the solution ideas. So we will not do coding. We will do just such questions. How do you sort a list of strings, for example? What's the best way to do it? No one knows, so that's what we'll be concerned with. So we will not do too much coding. We'll sometimes write code because you need some piece of code, but those will be just very probably just short snippets of some relatively simple ideas. So the list of our seminars is down here, and when you look at it, we'll get something like a lot of various questions which we'll come to just today. For example, how do you calculate this with your favorite programming language? You have n factorial, it's an exponent of n, you take twice logarithm of that, n is about 10 million, and maybe it is easy, maybe it is not. And that's it. For example, the task is a positive integer smaller than n, which binary representation contains exactly 3 ones. Produce all of those binary numbers and such things. So it's just a short example what we will do during the seminars. Now after that comes the exam at the end of the semester, and the exam is rather dreaded part of the whole subject, because there is a programming part of the exam. There is also a theoretical part, which is just your more or less standard oral part, where I ask you how do you, for example, search with the help of some search tree, or how do no idea how do you traverse a tree, for example, or something like that, and you'll have time to explain it. So that is standard, more or less usual, usual exam. And that is the programming part, which is an active programming. So you will come and you will sit in some suitable lab in this building, and you will be given a programming problem, and you will have again to produce a working code which solves the problem. It is typically about 100 to 150 lines of code which solves a particular problem. For example, I will give you an example after a while, or maybe during the seminars. And that has to be a correct one. What is important, nevertheless, is that again there will be 10 input data files which you will not know, and your solution must work correctly on at least 5 of the 5. So 50% success rate is the minimum you have to achieve. That takes some few hours. Typically, we have 4 hours for that, and that's it. In fact, what is important also that the programming part you can take any resources. So you bring in the lecture slides, the codes of your homework, pieces of, let's say, of Wikipedia or some algorithm sites or anything like that. When you bring it in, you can use it during the programming part as a source of your knowledge. To put together correctly the code, and then there is grading, where we total the points gained by solving homeworks, by solving the programming part, and by solving the theoretical part, and then there is grading, and then there it is. So it's more or less, very briefly, the overview what will happen. If you have any questions now or maybe later, you can ask, of course. So maybe I will directly go to the lecture slides. Today's lecture slides, there are the lectures, and today we have to talk about order of growth, which is a completely mathematical topic, so maybe I will a little bit put it aside, because we don't, on the other hand, do not have that much time, and concentrate on that complexity. What is it and what does it look like? So I'm going to present the slides for the complexity. One warning: I also teach a course of programming which takes place yesterday, and just not to scare you or your colleagues, it's a different course, but the first, that means this week lecture slides are the same for both courses. So if you meet somebody, or if it happens that somebody will say that those 2 courses are the same, there are same slides in the one course and the other one. No, they are not the same. We have just only at the very beginning these topics of complexity, because it's quite important topics, and then of course both courses diverge. Jump to the complexity of algorithms. You surely know that when you write a program, it is either fast or it is slow. If you have bigger data, if your data is small, then of course it is always fast. The machine is fast enough. But otherwise, when you are getting to bigger and bigger data, and everybody is getting to bigger and bigger data nowadays, so then you have somehow to distinguish between fast and slow programs, or between fast and slow algorithms, more importantly, and that can be done. Well, mostly it can be done by a so-called asymptotic complexity, which they say, what do they mean by this asymptotic complexity? The number of algorithm operations with respect to the growing size of input data, and you characterize a program or an algorithm by the complexity, and that complexity is not a number. You typically say, well, this is big, it is 50 meters high, that is 100 meters high, and you assign numbers to things to measure how big or how fast they are by one number. The algorithm is assigned a function, not a number, but a function, which is much complex object, so it's not obvious, and therefore they do not teach it in elementary schools. But it is worth it because it brings some clarity into the subject. So there is a growing function. What do they mean by that? Look at it. There will be some functions which, if you take a fast algorithm, what the function will say? The function will say, as our demands, typically as the data size grows, the program, when it is run on small data and then on bigger data and then on still bigger data, it will each time it will take some time to process the data, but the time needed to process the data will grow slowly. So, for example, if you've got I don't know, data of size 10, size of data, and there will be time of processing. So size of data, let's see, you have just 10 entries, something small, then you have 100 entries, 1,000 entries, then you are feeling bold, and you go to 1 million entries, and so on. So imagine you say, okay, this takes one millisecond. Then you go to 100, and then that takes two, that's millisecond, second, and when you get to 1,000 of data, you get to 10 milliseconds, and when you got to 1 million, it takes you half of a second of process the data, half of second. So you say, okay, it looks relatively nicely, isn't it? Well, when the data are small, it is done very immediately. When the data are getting bigger, big data, what can you do? Then you go to 10 million. And what happens is that you compute it in 2 seconds. Not that hard. Maybe, but who knows what the program does. That's one possibility. Or you can have another algorithm which does nearly the same thing. And in this case, when the size of data is 10, it runs also in 1 millisecond, and when they've got to 100, the size of data is 100, then they say, okay, we'll have 200 milliseconds, and when the data is 1,000, then it takes 2 seconds, and when there is millions, it takes 14 days, and in this case, it takes about half a year. So obviously the second one is trivially, you would not like the second one. And, but you might say the following, which I do not recommend. If we have small data, then they are comparable. If the data are a little bit bigger, we do not care, let's say. Or maybe we buy a faster computer. No, small data, buy a faster computer. Buy a faster machine. So, and you buy a faster machine, and when your machine is fast enough, then on some relatively small data, you can beat the original better original algorithm. So, all right, you might be quite happy for a while until the other guys also buy faster machine, and then you are back to original problem. But what is important was that the comparison is done all along this line. You look at this sequence of results, and you compare those sequences. That means you are in fact comparing a function. This is a function of data size, which is the few values are tabulated here. So you don't just take two values, it takes 2 seconds, it takes 4 seconds. You say, well, what happens as we go down the line here? That is important because in the future the data will grow, the data size will grow and grow. So of course you can easily predict what will happen. That is why we have these functions, or maybe we don't have them because we have them. Okay. So we compare the functions. Fast algorithms are described by slowly growing function, and slow algorithms are described by a quickly growing function. So that's a little bit maybe less intuitive, but nothing can be done about it. So that's the main idea of the whole presentation. So now maybe I can go into a few details about it. Have some examples of what is slow, what is fast, and how to measure it. The first example, we will have few very trivial examples. You have to find minimum and maximum in your array. Well, find a minimum and maximum. What you do? You scan the array and check each element of the array, and as you go, you update your minimum and maximum as it is stated here. If your element is smaller than minimum, then you update it, and you do the same with the maximum. Easy and very standard. So it is so-called slow algorithms because they have also a faster algorithm in their sleeve hidden, because look at the other approach. Now they say, all right, but now we are going not by comparing each element with the minimum and maximum, but now we proceed through the array by pairs. So you check the first pair, then you check the second pair, third pair, fourth pair, and so on. And in each of those pairs, you first decide which element of that pair is bigger. Either it is the first one, either it is the second one, is the smaller. So let's suppose for the moment that the first element is smaller. And if the first element is smaller and you are looking for a minimum of the whole array, then in that moment, you know that the second element of the pair, which is bigger, cannot be a candidate for the minimum, because the first element is smaller. So he might be the minimum, the second is bigger, cannot be the minimum. So you don't have to check the second element of that pair, whether it is minimum or not, so you can drop one test. It's unnecessary. So here it is more or less clearly said. If the first element is smaller than the second, than the next element, so in that case you check the first element whether it is smaller than minimum, and then of course you also check the second element, which is bigger, whether it is a candidate for maximum. Of course, 2 cannot be candidate for maximum, so you do not check it. What is the result? Here it is once more, the whole stuff once more as you go through the array. And what is the result of this analysis and this different approach? Here it is one more times coded. It is in Python. This is the header of this for loop. If you don't understand it, it doesn't make too big of problem, because they take your loop variable I and go from 1 to a length of your array -1, and there you can specify the step. So the syntax is rather simple. But that's just a digression. What is important then? Then I can skip over a few next few slides and give you this slide, which says we had this faster method, and how fast it is. We take one pair, and on each pair we perform only 3 tests. Because first you check whether the first or whether the second element is bigger. That's the first check. You say, well, 2 is smaller than 7. That is one test. And then you check whether 2 is smaller than minimum, and then you check whether 7 is bigger than the maximum. Total is 3 tests. So, and how many pairs are there in the whole array? Okay, the length of the array is n, so there is this number of pairs, more or less n over 2. The total is 3n, there is a formula, more or less 3n over 2. That means 1.5 n. So find min and maximum. Slow. You check each element twice if it is smaller than minimum or bigger than maximum. So there is check each element twice. Each element 2 times. So you do about 2 times n comparisons. Comparisons and fast, just faster. Check pairs. It is 1.5. It is 1.5 n comparisons. And in this moment, again, it is quite obvious that the second method is faster. But now, I have told you that you have to look at both methods, and to look at the speeds or execution times as a function of the size. So now it does not matter. How big the data are. The ratio between the speed is still the same. So no matter how big the data are, the ratio between the two is still the same. It is 1.5 over 2, which is 0.75, 3/4 or something like that. On the other hand, in this original small example, the gap between the two was getting bigger and bigger all the time, and quite dramatically, in fact. So what you generally tend to say that these two methods are more or less comparable. They have the same, let's say, asymptotic complexity. Because the ratio of the speed does not change with the size of the data. In this case, you have a different asymptotic complexity. Asymptotic complexity. So, all right. Let's have an example. So this just repeats what I have just drawn here on the blackboard. They say, okay, when you are computing minimum and maximum either by the original method or by the faster method, you get this number of comparisons which you have to do, and of course that number of comparisons, the ratio between the numbers is always the same. So they give you another example just to reinforce the idea. The problem is the following. You've got two arrays of the same size, and they ask you how many elements of the second array are equal to the sum of all elements in the first array. So what you do? There are various possibilities what to do, as there always are in programming, which we will see in a moment. But generally, without any programming, well, the sum of the first array is 4, so you check each element of B whether you get 4. All right, but there are various programming languages, in that number also Python, which give you very simple way of expressing your ideas, like here at the top. What you do? Well, you say, well, the problem is obvious. We go through the second array, and we check each element of that array whether it is equal to the sum of A. Obviously, that's what they ask you to do, and that's what you really did. And if that element is equal to the sum, you just increase your counter, and finally you return counter, and that's it. Well, the problem is solved. But the method is slow just because you here repeatedly evaluate the sum of A repeatedly. And repeatedly, you may say, well, maybe there is some maybe there is some optimizing compiler which once it evaluates the sum of A, it remembers it somewhere, predicting that you will be maybe asking for another evaluation. So next time they come into this sum, the compiler will say, the interpreter will say, it was previously computed, so I already know it, I will substitute it there. That's a different story. But it does not happen typically. So this is a slow method because simply this is repeatedly evaluated. If you are going to solve the problem, you will of course go for the second code, which you just first you compute that sum of A, and then you just refer to that one particular number. Now, of course, this is once more just schematically presented. Slow method takes element by element by element in the second array, and with each of that element, it goes through the whole first array, and with the next element, it again goes through the whole array, and so forth. The fast method, of course, is I probably don't have to comment on it, as it is obvious. So now when you go and you create your table of this kind, there is your size of the data, rather smallish data, and then they suddenly jump to million. The slow method operations, that is how many times you have to access an element in the array, it is somehow suspiciously big number, but it's correct. So you again do the ratio between the number of performed operations in both of slow and fast method, and you can again see that the ratio is not all the time all the same, is not constant. The ratio is growing. So you say, the fast method, the complexity of the fast method is smaller than the complexity of the slow method, because the complexity tells you that as your data grow, those who are better are getting really more and more better. So if you go with this to infinity, if you prolong this table down to infinity with still growing size, then this ratio will also grow to infinity, or if you invert it, it will converge to 0. So that's the meaning that somebody has better asymptotic complexity than somebody else. As the data are growing, it's getting more and more obvious who is better. So now maybe I will show you another example, which probably we will have to go relatively fast through it, but nevertheless I cannot do anything about it. The problem is as follows. It is somewhere, it is taken from the other course I have mentioned at the beginning, but I will probably incorporate it in this course as well. And what do they say? Given a sequence of n numbers, find a contiguous subsequence which sum of elements is maximum possible. What do they mean by that? Maybe the fastest way would be to run small examples. So I apologize for a very quick scrolling. I just comment out the pieces of the code I don't want. Let's have these done. And also let's have some printout. Otherwise, good. And there is this thing. Or print list. Okay, maybe it will produce something. It did produce something. Okay, it is, yeah. So what is the problem and what is the solution? The problem is easy. The solution is easy as well. We are given a sequence of numbers like this one. This seems to be better for explanation, the bottom one. I skipped the upper one. So they give you some sequence of numbers. You do not know what numbers will be there. And you are asked to produce, to find a piece of that sequence, that is contiguous subsequence, which has maximum sum of its elements. If all the entries were positive, then the task would be trivial. You would just add everything, and you will say, "Oh, here is my maximum possible sum of everything." But now, because there are negative values, then your of course. Your method is not obvious how to do it, because you say 4 plus 4 is 8. Good. But then you go, if you incorporate -1, the sum goes down to 7, so it is not nice. But then it is compensated by the 6 which you meet here. Aha, good idea. So the sum is 13, and now I see that it was not programmed correctly. Good. So I have found the problem in it, and you can see it as well, I hope. This is not working correctly. We should get 14. So let's 2, 4, 6, 10. Wow. So good. So there's a problem which has to be checked. Nevertheless, so before I go and maybe fix it, what is important, nevertheless, that is this really? Yeah. What is important is that we don't know, at the moment, we don't know how to solve it nicely. You can even see that when somebody comes and tries to solve it, they still can produce obvious errors, and that's all. Now maybe it's time to debug the program a little bit, because it did not discover this part. So it suggests that the problem might be in the bounds of the loop. So typically it's at the end. So what's going on there? The solution there is the solution. The cubic one produced best I, best j. So there it is listed. Best j is here. So I will take, I hope no more than 1 minute. So then I will not disturb you, and maybe we will fix it during the seminars. But it is rather tempting to correct it now. What the cubic solution? Thus it goes from I sum is I2 I don't see it. We are going from 10, 8, 4. We go from I, that goes from I to the length, and this goes from I1 to I2, that wow, does that help? That's -16, does not help. I don't see the problem at the moment. So if anybody sees the problem, please tell me. All right. Now, after I will continue with the original explanation I had in mind, and maybe we will discover what is wrong with the code. Nevertheless, aside from this problem, the code really does something, and there are obvious ways of solution. We are given this sequence, And then what we do is say, okay, we have to find a subsequence and to sum it. So let's take all possible subsequence, compute the sum of all those subsequence, and then just choose the maximum. That's exactly what's going on in the code, where they say, all right, you start with I1 in some particular range from 0 to the end of the list. So there is your list. Imagine it here on the table. So you start at the beginning, and then you set step by step. You try all possible beginnings of your subsequence, and in the inner loop you try all possible ends of your subsequence. So you move that, then move this by one, and again and move this with and each time you take the sum of your particular subsequence between the first and the second index, which is done exactly here. Computes sum of a list. No, sorry, it is this. It is here. The two loops are there. Then you take the sum of a list from I1 to I2. From I1 to I2, how does that work? I1 is there, I2 is there, and it typically goes between the stuff. I1, I2. So there's 0, 1, 2, 3, 4, 5, 6. So when you work from I1 to I2, then the I2 has to be bigger by 1 than the last element. So that should be correct. And then the check here, just the test just registers if you by accident find a bigger current sum, then you register it, and that's all. So you say, okay, fine, that might be working nicely. Then somebody else come in and says, well, let's do it in a more clever way. And maybe I will write it here on the blackboard. Let's have some different elements. 4, -1, 3, -2, -3, 6, 1, -5. So what you do if you are computing all possible subsequences, you say, okay, we start with 4, and then that sum is 4. Take this subsequence. Then you take next subsequence, and you add everything, but you don't have to add everything because already you know that the beginning has sum 4. So you just add -1 to your existing sum. So you can say, aha. The sum here is 3. Then you just add 3 to the which is 6. And you can produce sums without returning. So for all possible subsequences which start here, you just compute the sums. 4, 3, 6, -2 is 4, -3 is 1, 7, 8, 3, and there you go. And then you start here and produce the sum. The sum is -1. You just forget about the beginning, and again you do the same. -1, there is this. -1 plus 3 is, I don't know, very probably 2. -2 goes down to 0. -3 goes to -3. 6 -3 plus 7 plus 6, excuse me, goes to very probably 3 plus 1 goes to 4, goes to -1, and so forth. And then you start here and do again the same process. So if this length is n. Then, of course, you do n. Here you do n times you go through the list or through the array, or the length of the part you go through is getting shorter and shorter, but it more or less does not matter. So you do about n square over 2 operations. The original idea was a little bit worse because you in each time we consider any subsequence, we had to compute its sum independently. So the original method sum each subsequence, which is so-called brute force. Check the sum of each subsequence. Okay, how many subsequences are there? I mean contiguous subsequence. Well, any subsequence has a beginning and it has an end. So how many pairs of beginning and ends are there? So how many subsequences? How many subsequences are there? Are there? Obviously, and choose 2. In how many ways you can choose a pair of indexes out of n indexes? You have to choose 2 of them, and by definition, the smaller will be the beginning, the bigger will be the end. So it is on maybe plus n, because you can also start and end at the same point. Something like that. So that is obviously, you can say it is n times n minus 1 over 2 plus n, which is n times n plus 1 over 2, which is generally n square over 2 plus n over 2. What is important now, of course, is this square, because that is going to be a big value and n is going to be relatively when compared to n is going to be relatively small. So that is the number of subsequences, but when we are checking each subsequence and making a sum of it, we will of course not have to multiply the number of subsequences by its length. Of course, so different. How many subsequences are there? That's the number of subsequences. How long is a average subsequence? An average subsequence. Well, if it is average, then its length is n over 2. N over 2, so more or less some. So some will be longer, some will be shorter. This is not an exact computation. So because we don't do it typically when we talk about the complexity, so we drop the details. So an average subsequence. How long? How long is an average? It is n over 2. So now you've got this number of sequences multiplied by the length. So here you can say in total, the formula is not exact. In total, the method the method will do about n times n squared over some constant. That constant is before. I am not quite sure. I think that it will be 6 when you add everything. The method will do about this number of comparisons. No comparisons operations. Now, and that's equal to n cubed. So that's the original method. The second method, which is up there shown as a quadratic method, with a quadratic method. This has gone somewhere. There it is. This is quadratic. Of course, you can solve the same problem I'm talking about by just going through the array only once. Which now you might ask, why doing all these analyses when you can solve it in that simple way? How do you do it? Well, you just keep totaling what you've got up there. So you've got 4, 3, 6. This is not the best example. So let's use the example which is there on the screen and which will help us. So if you want the maximum subsequence and you find -4 at the beginning, you say, I don't like it. -4 is surely not a big value. There will be something bigger in the future. So let's start with 0. Then you come to 9 and say, oh, beautiful. So let our subsequence start here, and the sum is 9. And then we continue. We have registered 9. Now it is, and let's continue. Getting to -6, the sum drops to 3. But there might be some bigger values later, so good. So let's continue. Now value drops to 2, and now the total of the highlighted part drops to -1. But -1 is surely not good because there are some positive values already. So -1 this part cannot be part of any reasonable subsequence which might come later because there it's already negative. So you just drop and forget it and say, we again start from the beginning. And this is 2. This is 2 negative for us. So we remember the maximum we had so far, which was 9. And after this -3, we again start from the beginning with our counting. That means we just continue. But we remember that we had maximum 9. And now look at this value. It is -5. Okay, let's forget it. Keep 0. Come to next value. It is 4. Good. Remember 4. Take another 4. Drops to, increases to 8, drops to 7, nothing bad happens, plus 6, increases to 13. Aha, that is big, sorry, that is bigger than previous 9, so now you remember 13, and now you go to -8, that gives you 5, next -8, that gives you -3, so you say, it's already negative. Let's forget it. So let's not forget, but let's just register we had 13. And again, you move to the next and you continue exactly as we did before. So you can scan it, in fact, only once. And what the implementation wants to show you that there is a big difference between this originally very slow approach with this intermediate intermediate approach where we had some improvement, and the final approach which I just mentioned. So the slowest one is called cubic one because there is n to the cube of number of operation involved in the solution. The next one is called quadratic because there is a square of n in the number of operations, and the final one, the fastest one, is linear because it is linear. Let us see if we can somehow implement or just check where the problem was originally before we come to the final solution sequence. Length is high. So let's print it each time after each of those and run it once more. What will they say? Sum is we get we are in the I lost it completely. Working with negative values. Wow. Aha. All right. My problem is that I put there a random seed, and each time we will get a different sequence. So that maybe was not the best idea. On the other hand, I wanted to have a completely random situation. Yep, give them some nice seed, 130, and see what happens. Nothing extra happens. So everybody gets some 34. Yeah. If it gets out of the array, then they should produce some exception, I think. Yeah. You can see that it still produces nice error, as obviously in there are three methods. Each produces the output. The first two methods produce the same output, which is hopefully good. The third method is not correct, and the third method is this one. The third method is the cubic method here. So let's move to cubic method, and it does not go to the very end of the list. So there is our problem down there, where we have to go. We go to the end. The end is there. Well. I don't see it, to be honest. Do you see it? Yeah. Let's. Yeah, no problem. You have our machine. Oh wow. Some 34. 30. Some is 34, and very probably they have to register it as well. +1. depends on how it is now. Well, now it's fixed. Thank you very much. So there is it's a typical nice example what happens when there are difficulties with indexes. Nevertheless, now it works. So obviously we can go and check whether the result is correct or not. I have no idea. You have to start here with 5 and go up to the very end. Well, there are big values at the end, so it is not strange. As you can see, they can skip these minuses, which there are enough positive values around those negatives, so that you can total a long part of the sequence. So now I will switch off the output of the solution, and I will leave there only times, because the times are what are we concerned with. Sequenceless is good, and run it once more, and we've got there is another output, but that output is somewhere here. All right. So they printed out the output, and what is important are the times. The times of all 3 methods are completely the same, just because our data are really small. The next, or even the last part of the whole. Program presentation is that now we go and run it on bigger data. Run it or bigger data, which I have put there the values, the sizes. Here are the sizes. There are generators up there, and now we run everything on a list with 100, 200, 400, 600, 1000, and 1050 for some reasons elements. And then you will see why we leave out the cubic solution, and later on we leave out the quadratic solution. It so happens that, as you can see, as we are getting to bigger and bigger value, the cubic solution, it takes some time to compute. The linear is not affected whatsoever. It takes some time to quadratic solution to produce a result, but the cubic solution, you could see when they had 600 elements, they were in 1 second. Then they went to 1000 elements, and cubic went to 10 seconds, and now you can see that it is completely senseless, because we are in some kind of environment which simply is not totally precise. So that means that here and this value should be surely smaller. As bigger, it should be bigger than the previous value. If you make data a little bit more bigger, then you should get a little bit more bigger time. So maybe we can redo it. So make it more dramatic. So don't take list 1050, and let's make a list of 1100. And run it on that size, and run it one more time. No, it will. No, it will. Sorry, it will collapse. Excuse me. No. Yeah. So again, of course, the times will be a little bit more different each time we run it, but as the data sizes are growing slowly, and the cubic solution just takes a lot of time to finish. Now we going to 100, 100. The next one is we leave out the cubic solution, because when the length goes up to 10,000, the cubic solution will be really small. Because it is cubic, if you multiply the size of the data by 10, then you have to multiply the execution time not by 10, but by the third power of 10, that means by 1,000. This means that computing the size of 10,000 with cubic solution would take about 12,000 seconds, which is about 12,000 seconds. How much it is? 1,000 seconds is 4 hours, yeah. So that 4 hours, just imagine, while the standard linear solution runs like mad, let's say. Again, quadr is quadratic solution, which took 30 seconds to process with when there was still just one 10,000 elements. Again, quadratic solution it is. It contains n square. So when you multiply the size of data by 10, you have to multiply execution time by 100, which is square of 10, and you can see that it more or less works. When we had 1,000 elements, it took 0.37 seconds, and we multiply the size by 10, we get to 100 times longer execution. So that's how we do that stuff with cubic, quadratic, and linear solutions. So that is the difference. And anybody can, of course, now make their mind how bad it is when the data are getting bigger and bigger, of course. And this is 100,000, and that is still, of course, that is small compared to typical data you get in any kind of serious real world processing. So this that was this part. So now I jump back to slides to finish the presentation. As you can see, we are not through all the slides, which now I have to somehow present them in some standard fashion. We've got about 10 minutes left, so I will go through them relatively fast and give you the idea what's there. So when we have compared the methods of these two methods of computing, of comparing sum of one array to the elements of the other array, we have seen this. We have seen this table, again giving us the idea that the two things are not the same. Again, they just compare the first task we had, the speed ratio task one. What was that task one? We were finding the minimum and maximum by two methods. They were in fact more or less the same. The second task was just mentioned. We have this situation, bigger and bigger ratio of the speeds. All right. There is another example, which is concerned with searching in sorted array. If you go standard searching and you have to find something, they give you some value 993. You go through the list, find it there, and be happy. If they give you another value, you might be lucky and find it immediately. All right. On average, of course, on average you will be somewhere in between when they give you some value. So your time you spend on searching is proportional to the size of the array typically. Of course, when the array is sorted, you don't have to search linearly through the array. You can go for a binary search, find a 863. What you do, you look in the middle and say, aha, good. So our element which we have to find is 863. Which is bigger than 836, obviously, so you can forget about the whole first half of the array, and then you go to the second half, where you again take the middle element, which is 939, and you ask whether the element you have to find, 863, is smaller, excuse me, is smaller than the element you are looking at, and it is smaller, so you again forget the remaining part of the array. As you can see, you can very fast get down and locate the element you are originally looking for. How fast this can be done? In each step you divide the size of your problem by 2. You halve the problem, so you are taking a half of the array, 1/4, 1/8, 1/16, 1/32, and so on, as it is shown here. So you need logarithm, binary logarithm of the size of array, which is number of steps you have to do until you get to one single element, and that logarithm is a small number. So if you go for a linear search, take an average number of checks you have to do. It is proportional to the size of the array. It is about half of the size of the array. When you go for a standard binary search, in worst case, you just have to make this very small number of comparisons, and you can see that as this is growing exponentially, this is growing more or less linearly. Important is that this grows exponentially and this grows linearly. When you compare the two, again, obviously the complexities of the two solutions are much more different. So now that there is the table which gives you some other possible complexities, which we haven't met all of them yet. We have met linear and square and cubic in our examples. Here they give you the size of the data, and what is important is to know that when your complexity is big, it is enough to have very small data, and the time, the execution times are ridiculously big. So that's the main idea which this table tries to convey. And we have seen it, of course, in our experiments in Python. Now there is the part which just jumps to plain mathematics and talks about the function's order of growth. So now there are about 20 slides which try to remind everybody what is an order of growth, and generally what is an order of growth can be summarized very simply. If you've got two growing functions and you take their ratio, that's Fn and Gn, ratio Fn over Gn, take that ratio and ask what is the limit of the ratio as n goes to infinity. Limit of Fn over Gn when n tends to infinity. If that ratio, if that limit is infinitely big, that means the f divided by g is really much faster, it grows really much faster, and it is in different order of growth than Gn. It has different order of growth. On the other hand, if you take Gn over Fn, that of course when n goes to infinity, that is 0. So you can easily compare two growing functions just by taking the ratio and looking what they do at infinity. If on the other hand as n goes to infinity, if that ratio is some real constant, for example 22 or 17 or 1 typically is the most popular one. So if they are the same, if this Fn over Gn goes to a real constant, then the functions have the same order of growth. And when they have the same order of growth, you can say, well, they are comparable. One is 4 times faster than the other, and it will be probably that constant 4. If you go to bigger and bigger numbers, the ratio is going to be the same. You say they are more or less the same. So after that you can say, okay, so if we know what are the order of growth, if we can compare the order of growth of some functions, then you can, now I skip a lot of various very interesting slides. Then you can go finally, please bear with me now because I have to go. Now you can more scientifically define what is asymptotic speed of algorithms, how to compare the two algorithms. How do you compare? You say one algorithm is faster than the other if we describe each algorithm by a function. That function tells us how many operations that algorithm does when it is given this data of some particular size. Given those functions, you compare those functions and you say that one algorithm is asymptotically faster than the other if the ratio of those functions is appropriately either infinity, either 0. So I will probably return back to this point next time for a few minutes, because today we are already overdue. So I have to apologize for being too much involved in this. So what can we do? So very probably I will return to this next time, because I cannot do anything about it at the moment, and the details we will do details during the seminars which we will have to have in 340 lecture hall. So the practices are 340. So thank you for your patience, and see you after 15 minutes. So that's it.